Okay, so today we'll finally define all the various types of singularities in the minimal model program. So let's just review the definitions very quickly. So if we had some log pair x comma delta, where delta is some divisor, some ai di, and we assumed in the definition of log pair that kx plus delta is Q Cartier. Then we've defined the discrepancies of a divisor E, say, by taking a resolution and writing f upper star kx plus delta equals ky, and then we had to give some correction term, and that was our discrepancy. Or let me write it this way. And so this number was the discrepancy of E. And then we defined the discrepancy of the pair to be the infimum over all exceptionals, over all log resolutions of these E exceptional of these numbers. And then we also had this total discrepancy where we dropped the word exceptional here, where you look at all divisors, including the ones that possibly are on X itself. Okay, and then there were a few things that I left as exercises for computing discrepancies. Maybe the most important one I'll recall right now. Okay, maybe there are two. So exercises. One was computation of the discrepancy of the exceptional divisor of a blowup. In terms of the multiplicity of z along the divisors. I won't use the exact formula today. I'll just mention it briefly at one point, so I won't rewrite the formula. And then two, which we'll use a lot, was this observation that if you have a proper birational map, if you have a proper birational map f from y to x, and you have some divisors, delta y and delta x, such that the push forward of delta y equals delta x, and the pullback of kx plus delta x is ky plus delta y. So you can think of this as there are no the only discrepancies are somehow coming from the divisor itself for this map f. Then for any prime divisor, the discrepancies of the pair for y are the same as those for x. So for any p lying over x. And the one thing to note here is that when p, and this we'll use all the time in some computations, so when p is itself an exceptional divisor of f, then the discrepancy so that then p is actually a divisor on y, and it's contained in this delta, because when we pull back, we're going to have some contribution from the exceptional in our pullback. And so whatever this divisor is, since it's a divisor that's actually on y, then its discrepancy is just minus the coefficient of this p in delta y. And so this tells us that if we care about the discrepancy of some particular divisor lying over x, then our strategy to understand it is to find some kind of blow up or some partial resolution. Y doesn't have to be actually smooth here, but just find some proper birational y that contains that divisor. And now the discrepancy of that divisor becomes part of the coefficients of the pair on y. So this will come up a lot. Okay. So the first thing we're going to do with this, or maybe a lot of things we'll do with this, a bunch of observations or computations that are useful, and just to get a feel of how discrepancies behave, and to lead to the correct definitions of singularities that we can work with. So just like before, we'll write delta sum of ai di, and then and assume that x delta is a log pair. First observation is that the discrepancy, this discrepancy of the pair, so this minimum over all exceptionals, is at most 1. So because we're looking at a minimum, we just need to show that there's always some exceptional with discrepancy 1. And to do that, we just use the case of surfaces. So just pick some smooth codimension 2 point of x away from delta. Everything's normal, so we can do this. And then because we're at this codimension 2 point, we can localize there, and then we get the local ring of a surface. So if we want to compute some discrepancy lying over that point, of some exceptional lying over that point, we can compute it on the surface. And so assume that we just have x and a smooth point. So x is a smooth surface and a point. Then we can consider the blow up of a point at a surface, which will be the generic point, like the generic model of the blow up of x at the closure of this codimension 2 point, and then just compute explicitly a of the exceptional of this blow up on a surface, and this is 1. So if we're just blowing up a smooth point on a surface, you just compute, because using that e squared is -1, that the discrepancy of that divisor is 1, and we can always get something that looks like this on any of our pairs by just blowing up a codimension 2 thing that's contained in the smooth locus. and that's away from delta, so we can ignore the divisor completely. So that tells us the discrepancy is at most 1, because we can always find these divisors with discrepancy 1. The next one, a little more subtle. So if you ever have that the total discrepancy is smaller than -1, then we can actually find a divisor whose discrepancy is as small as we like. Oh. So then there exists some prime divisor P lying over X, whose discrepancy smaller than -k for any k. So for any k, we can find such a P. Is really what I should have written. Or another way of saying it is that if the discrepancy is smaller than -1, then it's actually -infinity. So because it was this infimum over all prime divisors. So in particular, this says that if you want to have well-behaved discrepancies, not only do you need all the discrepancies of exceptionals to be at least -1, otherwise things get arbitrarily bad, but here we're looking at the total discrepancy. So it says that also your divisors shouldn't have coefficients bigger than 1, because remember the discrepancy of a divisor in our pair is just minus its coefficient. So yeah, so if we want to have well-behaved discrepancies, we should only look at divisors whose coefficients are less than or equal to 1, and this was half of our definition of a boundary. Okay, so let's see why this is true. So we're going to use this exercise. So let's pick some E lying over X with discrepancy equal to, say, -1 minus some number C, where C is strictly bigger than 0. So now we want to pick just some map F from Y to X that contains this E. And then we'll pick, or another way to say it, maybe another way to say that E is just a divisor on Y itself is to say that the center on Y of this E is a divisor. Whatever that divisor is, it's at the generic point is just the same as E, and so we can think about the discrepancies on Y or any other model that contains this E. Okay, so pick such a Y, and then let's write down F upper star kx plus delta equals ky plus delta y. So define delta y to be the divisor that makes this true with the push forward being delta. So just add in the strict transforms for this F, and then add in whatever multiples of exceptionals of F you need to make this equality true. So we're basically adding in minus the discrepancies of the exceptionals, including this E itself. So then the observation by the previous exercise was that the discrepancy of any prime divisor on x is the same as that on y. So we can compute on this y. But we also know that for this particular divisor e, the discrepancy not only is the same, but has to be a coefficient of this delta y. So delta y has to be minus the discrepancy, so 1 plus c times e plus maybe some exceptional stuff and some strict transforms. Okay, but now we have our e as an actual divisor with coefficient strictly bigger than 1. And so now we can start blowing up to compute discrepancies or to produce divisors with smaller discrepancies. And we're just going to blow up on a point of this e, maybe in the smooth locus of y, on some codimension 2 point. So just like before, we're reducing it to the case of surfaces, basically, by looking at blowups through centers of codimension 2, because the discrepancy only cares about the generic point of the divisor, so we can localize at this codimension 2 point, and so we get a 2-dimensional ring. And so let me just draw our picture. So on y, and maybe after localizing, we just have some curve e, and it has discrepancy -1 minus c. And now we're going to pick some point there. We'll call it z. There's really some codimension 2 subset, but that's contained in the whose generic point is in the smooth locus of y and in the smooth locus of e as well. And now we're going to blow up this z. So now let y1 be the blow up of z. And now we're introducing a second exceptional curve. We'll call it e1. So now we have our e, or its strict transform, but again, we only care about the generic points. So our e comes with coefficient minus, or with discrepancy -1 minus c, because it's still part of our boundary. And then we have this new exceptional e1, and we want to compute its discrepancy. But now we're computing on a surface again, because we're at this codimension 2 point, so we can just localize there. And so now we can compute on the smooth surface, and we can compute that ky plus 1 plus ce. Let's call this blow up mu1. We can compute this thing when we pull it back. Well, for ky, when we pull that back, we have to subtract the exceptional. We got kx minus the new exceptional e1. But then when we pull back e, since e goes through this point that we're blowing up, pulling back e gives us 1 copy plus c of the exceptional. So here we get kx minus e from just pulling back ky, but then plus 1 plus c, sorry, minus e1, plus 1 plus c e1, and then plus, well, that's it. Yeah, then plus 1 plus c e, the thing we already had. So then we have this e1, and then we have this minus e1, so we just get plus c e1. Okay. So if we replace, if we take the pair on y1, that's again defined like up here where it's the divisor, so that when you pull it back, you get the log canonical upstairs, and so that the push forward is our divisor downstairs. Then here we have delta y1 is CE1 plus 1 plus CE in a neighborhood here. So again, we're picking this generic codimension 2 point that avoids all the other divisors. It just sees this one E localizing there. So we've ignored all the rest of our divisors. So in a neighborhood here, we just have that our boundary is CE1 plus 1 plus CE, and our divisors intersect like that. So yeah, so then here our discrepancy for E1, which is the same as the discrepancy of E1 on X because we chose the right divisor here, is its coefficient minus C. But now we keep going. Now we take Z1 here, which is the point at this intersection. So that's going to be another codimension 2 point on X. So its closure will be some codimension 2 subvariety that we can blow up. And now we can blow that up. So let Y2 be the blow up of Z1 on Y1. And now what's going to happen? Well, when we blow that up, we have our E still with discrepancy minus 1 minus C. We have our E1, whose discrepancy we just computed was minus C. And now we have a new component, a new exceptional, which we'll call E2. And now the same exact computation tells you that the coefficient in this pullback of E2 is 2C. And so same computation tells us then that the discrepancy of E2 over Y1, but again is the same as X because of we chose the right divisor, is minus 2C. Essentially, because every time we're pulling back this canonical, that will contribute one copy of the exceptional. That'll subtract one copy of the exceptional. Then E and E1 will contribute 2 copies of the exceptional, so the whole thing will go up by 1, and so you get that. You just have this C left. So this is minus 2C. And now we keep going. Now we blow up this point, and this introduces a new divisor with discrepancy minus 3C. And we keep making our pair on delta to be exactly this pullback divisor so that the discrepancy is the same as that on X. So in this way, we've constructed a sequence of blowups with discrepancy of this AK, which is the exceptional of the kth blowup, equal to minus K times C, but C was positive because it was this number, so that E was an exceptional divisor whose discrepancy was minus 1 minus C. And so our discrepancies get arbitrarily smaller, and so our total discrepancy is minus infinity. Okay. Sorry, that was kind of maybe a little bit of a mess. Are there any questions? Okay, so that tells us that if we want to have well-behaved discrepancies, we should only look at pairs whose total discrepancy is at least minus 1. Okay, and maybe the next observation is to compute the discrepancy on a normal crossings pair. So if X comma delta is simple normal crossings, and let's say that delta has coefficients less than or equal to 1, maybe delta is a boundary. And so in particular, X is smooth because it's part of being simple normal crossings. Then the discrepancy of this pair can be computed as follows. It's the minimum of, well, we have some contributions coming from the divisors, sorry, coming from blowing up the intersections of the divisors. And so the same way we computed here, what happens when you blow up the intersection of two divisors that are in your boundary, like in this blow up here. So you can compute there the same way, and you'll get that the contribution is that the discrepancy is like 1 minus the coefficient of the first divisor minus the coefficient of the second divisor. So anytime we blow up this intersection of two divisors that are like normal crossings, then that's our contribution. So our discrepancy has to be smaller than that. So we have a contribution of the form minimum over divisors that intersect of the numbers 1 minus AI minus AJ, because that's the discrepancy of that exception, of the exceptional we get when we blow up there. And then we have another contribution coming from the divisors themselves. So we have the discrepancies. Yeah, and so we get minimum of 1 minus AJ, so the coefficients of the divisors themselves, and then also 1, because we already saw that that's the biggest the discrepancy can be. Okay, so that's the claim that for a simple normal crossings pair, you have this really nice formula just in terms of the coefficients of the divisors. So I'll say just a few words about how you actually prove this, but I want to remark on some special cases. So if the boundary is empty, then we get that the discrepancy of a smooth of X, which is just smooth with no boundary, is 1. And so in particular, this is we kind of already saw this when we made the claim that smooth varieties had terminal singularities. So this is one way to prove this is to use this formula. And then if delta is reduced, so it's just an actual Cartier divisor with coefficient 1. If delta is reduced and smooth, so we just have some pair, just a single smooth divisor, then the discrepancy of this pair, well, now we don't have these intersection terms. We just have this one term that's like 1 minus the coefficient, and so we get 0 for the minimum, because the coefficient's 1 if it's reduced. And then if delta is reduced but not smooth, so it really has multiple components that intersect, then we do have these terms that where we're subtracting 2 coefficients, where we can blow up the intersections, and then we get the discrepancies minus 1. So these are kind of the cases we'll get when we're doing resolutions, when we end up in the log smooth case. Okay, so the idea to actually prove this, which I won't actually do, but the sketch is that let's just call this number, let's just give it a name. This minimum, let's call it R of X comma D. So the fact that the discrepancy is smaller is a computation, just like above, where you just compute that there are divisors with these discrepancies. So again, if you blow up the intersection of two prime divisors, we'll get an exceptional with discrepancy 1 minus AI minus AJ. And if we just blow up a point, like a codimension 2 point on our divisor DI, then we'll get this 1 minus AJ term. So we find divisors that have these numbers as their discrepancies, and that automatically tells us that the discrepancy of the pair is smaller. And now for the other inequality, we need 2 facts. One, we'll use the formula for blowups. This is the only place that really appears. Discrep. Nope, that's not right. For discrepancy of blowups, And then the following fact, which I'll write as a lemma, if E is any divisor lying over X, then there exists a sequence of blowups such that E is a divisor in this Y. So it's this sequence of blowups, Y equals the last one, xm to xm minus 1, such that this E appears on this blowup. So a priori, E by definition is just a divisor on some proper birational Y. And this is saying that maybe that proper birational Y isn't a sequence of blowups at, say, maybe here I want to say at reduced centers. But we can find some sequence of blowups so that E is actually a divisor there. And so then we use our formula for this discrepancy for blowups plus induction on this M to get the other direction for this inequality. To get to get that that the discrepancy of, or sorry, to get that A, the discrepancy of this particular divisor is greater than or equal to R. So this is the only place that this formula for blowing up a smooth variety for that discrepancy comes up. Okay. Any questions? And maybe I should remark this lemma. I phrase it geometrically, but it's actually a like a ring theory lemma. Like basically, you say, given any discrete valuation ring in the function field of X, you find some sequence of blowups so that discrete valuation ring is the complete or is the local ring at some codimension 1 point of the blowup. So it's really like an algebra kind of thing. Okay. And now we have a corollary that lets us compute discrepancies using a single resolution. Because in the definition, we have to really look at all exceptional divisors of all resolutions, but we would like to be able to actually just use one resolution. So proposition. So X delta will always be a log pair, so I won't write it every time anymore. So there exists, unless I say otherwise. Okay, so there exists a resolution okay, so the first part of the lemma is there exists a log resolution f from y to x with exceptionals ei such that the divisor we get by just strict transforming each of the divisors on x, so on our boundary. So let's say such that this divisor is actually smooth. And then if on this resolution, if we pick such a resolution and we see that all the discrepancies of the exceptional divisors on this particular resolution are greater than or equal to -1, are above this threshold where below which things just go wild, then the discrepancy is given by just this particular resolution. Okay, then the discrepancy of this pair is the minimum of the particular discrepancies of exceptionals we see on this single resolution, and the things we know we have to have because we could blow up a codimension 2 point on D itself. So we have these 1 minus AJs and 1 because that's just the minimum always. Okay, so this is great because it tells us that that if we're in this good case where the discrepancies don't go wild, then we can compute things on just one resolution. So given a log resolution that exists by Hironaka, then just blow up the intersections of these strict transforms to kind of separate them so that they don't intersect, and so they're each smooth. So maybe the picture is maybe I blew up so that I have D1 and D2 over here. So now they're all smooth and normal crossings, but they're intersecting, so the whole thing isn't smooth. So now I just blow up again to separate them, so all my strict transforms are actually just smooth. So I might have more exceptionals than I need, and that's the point. The point is that we know we might have to do these further blowups to compute discrepancies, and this proposition is saying that to compute all the discrepancies you want, you only have to go as far as blowing up the intersections. Once your log smooth, then the only extra divisors you might need to see are the ones coming from blowing up intersections to separate the branches, which kind of makes sense if you think about how we showed that if A is smaller than -1, why it's actually why the discrepancy is -infinity was exactly by looking at these divisors that we got by blowing up these intersections. So it's saying kind of if that doesn't happen, then this is all you need to do. Okay, so then, so now just like before, we'll let, given such a resolution, we'll pick our delta y such that these two things are satisfied, so we can compute discrepancies here. And then note that if we let bi be minus the discrepancy of our exceptionals for this resolution, then these are exactly the coefficients of ei in delta y as observed before, or really by definition. Okay, so then we know that the discrepancy of x comma delta, well, it's going to be the minimum of all exceptionals lying over x, and the exceptionals lying over x are either exceptionals lying over y or the ei. So it's the minimum of the discrepancy of the pair with y or of the contributions from these BIs, from the actual discrepancies of these exceptionals EI. So if I put total discrepancy on both sides, then I wouldn't need this term because the total discrepancy already includes the minus BIs. But the discrepancy of y only includes further exceptionals since the EIs aren't exceptional on y. Okay, but now this y delta y is some normal crossings divisor. So now we can use our computation in the normal crossings case to see that the discrepancy y delta y is a minimum of terms of the form, well, I have things coming from these b's. I also have things coming from the a's because they're also in delta. The strict transforms of delta are in delta y. So I also have things coming from those coefficients. I have things coming from the intersection of exceptionals and strict transforms. So these will be numbers of the form bi minus aj. I also have things like the intersection of two exceptionals. But I don't have anything of the form 1 minus aj minus al. Because of this assumption that the strict transform is actually smooth, that we've blown up enough to actually separate the branches of the strict transform. And so because two divisors in the strict transform never intersect on our y, I don't ever have to consider these type of terms. And that's the key point. And so now we just note that bi by assumption is less than or equal to 1. That was the assumption in our proposition, that for this resolution, the discrepancies of our exceptionals are at least minus 1. And so our coefficients are at most 1. And so then we just see that each of these terms are bigger than minus bi, because so 1 minus bi is positive or is non-negative, and so minus bi is less than or equal to any of these terms. Yeah, and so that tells us that in this minimum, we just need to consider the 1 minus aj's and then the minus bi's, which are the discrepancies of these particular ei's. So okay. So, and let me remark here that if delta is 0, so there's no divisor, then there's no condition on our resolution. We just take any log resolution, and so then this tells us that that in the case that we don't have a divisor, then for any fixed log resolution, if the discrepancies of exceptionals, now I don't have a divisor, so just x, if these discrepancies are greater than or equal to minus 1, then the discrepancy of x is just the minimum of these exceptionals. So in the absolute case, things are easy. You just pick any log resolution, and if you know you're in the situation where the discrepancies don't go wild, then you've computed the discrepancies. Then you've computed the discrepancy of x in the absolute sense. Okay. So this is maybe another a different proof of the fact that having say KLT having terminal singularities or canonical singularities was independent of the choice of resolution, because you could phrase it in terms of all your exceptionals are always bigger than 0 or greater than or equal to 0. So in particular, for any resolution, then you have this bound satisfied, because you only need to be at least minus 1 for this bound to apply this proposition. And so this tells you that in the terminal or canonical case, then the discrepancy is computed by any log resolution that you want. Okay. some corollaries. So there's some semi-continuity that's useful. So if X delta is a log pair, and L is some Cartier divisor, and take L0 is some fixed member of this linear series, and LG is some generic member. So in particular here, we're assuming that L moves, that it has at least two different members. Then the discrepancy of delta plus CL0 is less than or equal to the discrepancy is less than or equal to the discrepancy of X delta plus CL generic. Intuitively, this should make sense because the special member of the linear series should have worse singularities. This L0 should be more singular than the LG. And so the discrepancy should be smaller because smaller discrepancies are more singular. Okay, and the proof. So again, we're going to pick some resolution where we can compute. But here we want to adapt it to this divisor L. So pick some log resolution where one, when we write down this F upper star L, we can write it as some B, some fixed part, plus some moving linear series. So sorry, F upper star of the full linear series, where this moving part is actually base point free. So resolve until your moving part is base point free. So essentially, you know L has a moving part because we're assuming there are at least two divisors in our linear series. And so L will on X will split up as some fixed part plus some moving part, but the moving part might not be base point free. But now we can resolve, we can blow up all our base points, blow up all the base loci of the moving part. And now upstairs we'll have some exceptional stuff plus some stuff that comes from the fixed part downstairs plus this free part. So basically take our resolution so that we made the moving part of L actually be base point free. And then the usual conditions to compute. So let's say the strict transform of delta is smooth. So again, separate out all the branches of delta, not just log resolve them. And then 3, this whole thing is normal crossings. Okay, so resolve until these things are satisfied. And now I won't write out the full argument, but the idea is that you use a couple of things. So now we can compute discrepancies on this resolution. And for our L0 on our LG, these are these moving divisors in our linear series. We can see that the discrepancies, so write down, so to do this, we have to write down like F upper star KX plus delta plus CL lambda, where lambda is either 0 or G. It's either the special or the generic. Pick our divisor upstairs to allow us to compute. And now the point is that we can compute, we can, the contribution coming from L, we can pick from this base point free series. So the point is this delta Y will contain B itself, like, or like we'll have some piece that's supported in B, some piece that's supported on the exceptionals of the resolution, and then some piece that's coming from the strict transforms of delta. We'll put all of that inside of delta Y. And then the moving part, when we go from L0 to LG, the only part that changes is the moving part of the linear series L. So the only thing that changes in our divisor upstairs is the moving part of this linear series F upper star L, which we've assumed to be base point free. in our resolution. So now we have our pair upstairs. That's delta y plus a multiple of this base point free divisor. But now we have Bertini theorem for base point free divisors implies that fg is smooth and the whole thing is normal crossing. So let me write it more generally that that delta y plus fg is simple normal crossings. So now we can compute the discrepancies of our pair downstairs using this delta y plus cf lambda. We also know that generically this is simple normal crossings, so we can compute it from the coefficients. That was our lemma about simple normal crossings. So for this thing, so now our previous lemma implies that, or the previous observation about simple normal crossings pairs implies that the discrepancy of y delta y plus fg is we can compute it, well, if you actually look at the thing, so we can compute this as minus the maximal coefficient. Let me give a notation. Let's say C of G, where C of G is the maximal, or just more generally, C of lambda is the maximal coefficient of an exceptional divisor inside this delta y plus f lambda. And so for our generic one, because we have something simple normal crossings, then we just compute it in terms of this maximal coefficient. That was our previous simple normal crossings case. And now for our special one, and now we use semi-continuity of multiplicities. So on the other hand, when we go from our generic one to our singular, to our L0, which might have some singularities, then the multiplicity of our L0 along wherever we're blowing up to produce y might get bigger. And so the coefficient of the exceptional gets bigger. And so this tells us that the coefficient of the maximal coefficient of the exceptional is greater than or equal to CG, that the coefficients of the exceptionals can only jump up when we specialize some special member of our linear series. And so the discrepancy can only go down, because then the discrepancy of y, well, it's same as x, with the special one is less than or equal to this minus C0. It might be even smaller because maybe for L0, we haven't blown up enough. We don't have a normal crossings resolution. We might have to blow up even more, so our discrepancy might be even smaller, but it's at most minus C0, which is less than or equal to the discrepancy of LG. Okay. So I wanted to sketch out this proof, just to kind of give a feel for how all these proofs work. That you take some resolution, you find the appropriate divisor, and you pick the appropriate properties for your resolution to be able to apply these previous computations to your setting. Okay, finally we can give some definitions of all the different singularities. So okay, so we'll say our pair is we'll make a table is terminal if Let me just write them all in a row. So we have, as we go down, we get a more general class of singularities. So terminal is contained in canonical, is contained in KLT, or Kawamata log terminal. Is contained in purely log terminal, which is abbreviated PLT, is contained in log canonical, which is abbreviated LC. If the discrepancy of x delta is equal to or sorry, not equal to, there are going to be inequalities. If the discrepancy is greater than 0 for terminal, greater than or equal to 0 for canonical, for KLT, we want it to be greater than -1, and we want that the round down of our divisor is 0. Or I'll say is less than or equal to 0, because here we're not assuming a boundary yet. And then for PLT, we just have the numerical condition on the discrepancy. And then for log canonical is greater than or equal to -1. Okay. So those are the definitions. And also, so we saw kind of two things that motivated this definition. The first one was that whatever class isn't log canonical, as soon as we get non-log canonical singularities, then the discrepancies don't tell us anything. So the discrepancies are completely meaningless for non-log canonical pairs because they go down to infinity, to -infinity. And then the other thing was that when we do have log canonical pairs, then we can compute discrepancies using a single resolution. Because if the discrepancy is greater than or equal to -1, then in particular, for any resolution, the assumptions of this proposition will be satisfied. So somehow the log canonical are the largest class of singularities where we can talk about discrepancies in a meaningful way. Terminal and canonical, we already saw. The only difference here is that now we're still allowing a divisor delta. And so there's going to be analogs of our theorems that originally, or propositions that originally motivated the definition of terminal and canonical in terms of discrepancies, which was about sections of the canonical divisor. Now, if I have a pair that's terminal or a pair that's canonical, this is telling you something about how sections of the log canonical divisor kx plus delta relate to sections of the canonical divisor kx upstairs. There's also maybe the other observation is that for these log versions, for these KLT, PLT, and log canonical, if you write everything in terms of the log discrepancy, which if you remember was just defined as the same thing as the discrepancy, but you add 1 to it. So log discrepancy is 1 plus a. Then these KLT, PLT, and log canonical are the same as the log discrepancies being greater than 0 with our round down condition, or just greater than 0, or just greater than or greater than or equal to 0. And so this from the point of view of log discrepancies, then these log terminal and log canonical are really the analogs of terminal and canonical for no divisor at all. So that's a reason for the naming. And then also this observation tells you that for log canonical, you have the analogous result that says that log canonical sections downstairs are the same as log canonical sections upstairs if you add the exceptional divisor. So that's this log discrepancy was a thing you get where if you write down f upper star kx plus delta is equal to ky plus sum of the reduced exceptional divisors plus the strict transform. So I'll just call it a B divisor of discrepancies. And so if you write things this way, with where the log discrepancies contribute to this B, because I've added the exceptionals on the other side, then this, again, the same argument from that proposition from 2 classes ago tells you that log canonical equals that your proj of the log canonical ring of this ring are ky plus plus our exceptionals plus our strict transform. Or really what I should say is that the push forward of the appropriate multiples of this divisor is the log canonical sheaf downstairs. But anyway, so in that sense, it generalizes. Our original motivation for even defining canonical was that they were the class of singularities where the sections of the canonical divisor were preserved. Log canonical are the class of singularities where the sections of the log canonical divisor are preserved, as long as you always add all your exceptionals to your boundary every time you take a birational map. Okay. Some more remarks. So there's another class that we'll define very soon called DLT, divisorially log terminal, but the definition is a little more subtle, so it doesn't just fit into this table. And this contained in log canonical, and it's more general than PLT. Essentially, okay, so I should just say all my remarks to then explain why we need DLT at all. So kind of what's the use of all of these things? So for terminal and canonical, we already saw where they came from. Terminal are the singularities we get when we start with something smooth and apply an extremal contraction. Canonical are the singularities on proj of the canonical ring. Log canonical are motivated 2 different ways. They're either singularities on proj of the log canonical ring, but they're also the largest class of singularities where we can work with discrepancies. KLT is a little more subtle, so KLT singularities, they are the singularities that come up when you take extremal contractions for the log minimal model program, which I haven't stated formally yet, but closed undertaking extremal contractions. So maybe kx plus delta extremal contractions. And we're going to prove the Conan contraction theorem in this full setting of KLT pairs. That's going to be one of the main results. So I'll defer to then to actually specifically define a kx plus delta extremal contraction in the log minimal model program. But these KLT singularities are kind of the natural class for that you get from extremal contractions there, but also they're well adapted for vanishing theorems, which is the next thing we'll do, which is one of the reasons why that's what you need to have a Conan contraction theorem that looks the same as the case of a smooth variety. And essentially that's where this rounding down condition comes in. So this rounding down condition is just saying that there's not a divisor with coefficient 1. because we know all the coefficients have to be at most 1 if your discrepancies are bounded by -1, and so this is saying like you can't have a divisor with coefficient 1, so your total discrepancy can't be -1. And that really comes in proving vanishing theorems, that you really need that condition for vanishing theorems to be true without extra assumptions. And then PLT, these are good for induction. Having these divisors with coefficient 1 lets you induct. Specifically, what I mean is if you have a PLT pair with the round down just a single divisor, let's say S, this is some irreducible divisor, then we have a more general version of adjunction, which we'll probably discuss in more detail at some point in the class. But then adjunction implies that kx plus delta restricted to S is equal to kx plus theta and essentially here theta is just defined as the divisor that makes this statement true, because you know that delta can be written as S plus stuff with coefficient smaller than 1. And so we know if we put like kx plus s restricted to s, then at least on the generic point, we get the canonical of s. There might be some singularities, some issues coming from singularities. And so what we know is that kx plus s restricted to s is the canonical of s plus some contribution coming from singularities of s. And then that's included in this theta. But then there's also a contribution coming from the other part of delta that's also included in this theta. So this theta includes both singularities of S and the contribution from the divisor that's not contained in S. But the upshot is that x comma delta PLT implies that S comma theta is KLT. Because now in this adjunction, we've kind of lost the only divisor with coefficient 1, and then you have to do some kind of computation of discrepancies to see that the discrepancies of S comma theta are all strictly bigger than -1, because, well, any divisor on S comma theta you can kind of try to get by taking some larger divisor sitting over X and comparing discrepancies. But the point is that if X comma delta is PLT, then S comma theta is KLT. And so these PLT pairs are the ones where you can run induction on dimension. So you can try to prove statements about x comma delta and a neighborhood of S by restricting to KLT pairs in one dimension lower to this S comma theta. In the last 2 or 3 minutes, let me just give the definition of DLT. I guess I should have remarked, the other thing I wanted to remark is why don't we just work with log canonical pairs all the time? And the issue is that just the gap from log terminal to log canonical is huge. The log canonical pairs are much more singular. Vanishing theorems just don't hold, and maybe the first kind of fundamental thing you see is that log canonical singularities are not rational, and this we already saw in these example of where you can contract a higher genus curve on a surface to produce a log canonical singularity, and so not only does this never come from an extremal contraction, but the geometry is much more, like cohomologically, it's much more complicated because now you have cohomology of the structure sheaf along your exceptional divisor. And so you can't just compute cohomology on a resolution, and you really need to like think about higher push forwards. So that makes log canonical singularities a lot more complicated. And this class of DLT singularities is supposed to be kind of some in between that bridges from log canonical to this one of these log terminal cases, the PLT or KLT. And so the way proofs about log canonical pairs often work is that you find some small resolution that's DLT, and that'll be one of the corollaries of knowing the log minimal model program, is that we can find some small resolutions that are DLT, and then we can use some kind of perturbation arguments and continuity results about discrepancies to perturb from this DLT case to this log terminal to these other log terminal cases, and then try to track what happens when we do these kind of small resolutions and perturbations. So that's where this DLT case comes from. And let me just give the definition as the last thing for today. If x comma delta is a log pair, and now we really want to assume that delta is a boundary, meaning that the coefficients are between 0 and 1. So recall this is just the definition of a boundary. Then we'll say that it's DLT, or divisorially log terminal, if there exists some closed subset Z such that 1, x minus Z with the pair delta minus Z is simple normal crossings. And 2, for any divisor E lying over X with center contained in Z, then the discrepancies for this divisor is strictly bigger than -1. So basically, this is saying that you don't have that all the discrepancies are strictly bigger than -1, but that you have this nice locus that's simple normal crossings, and then there you might have discrepancies that are strictly -1, so they're in this log canonical case. But everywhere else where the singularities are worse than simple normal crossings, then you actually are in this like PLT case where the discrepancies are strictly bigger than -1. And so this is why it's kind of some hybrid in between where you've put all of the issues about log canonical singularities into a normal crossings piece, and then everything that's left is in this PLT case where we have a lot more results. Okay, so I'll stop there for today.